For those of you that need more information about back dilution, well, guess what? That's what this video is going to be. So if you feel comfortable with the concept of back dilution, skip me. Go to the next video. But if you maybe want a quick review of a back dilution just to see what we're talking about and how to incorporate these calculations in your calculations that are required for the lab, then this video is for you. Also keep in mind that the back dilutions will also be presented in the upcoming assignment. So if you want to make sure that you can get the best grade possible on that assignment, at least make sure that you watch maybe the first example that we do of back dilution, just to make sure that you're on the same page that we are. All right, so let's say that in a laboratory we run a sample, and that sample gives me a very high absorbance or signal. I'm going to put signal here. And let me erase that bracket because we're not talking about concentrations. We're talking about signal. So that's a problem, right? We've already discussed these concepts of the standard or the samples running higher than my standard, and I never want that to happen. I want my samples to be in the ranges that my standards are. So we said that one of these solutions is to weaken that sample down and then rerun that sample. So let's say that I do that, and I come in and I go into a laboratory. I find this sample that runs really high. It says over maybe on the software, or just extremely higher than the highest standard, and I know there's a problem. So I go back to the wet lab and then I dilute that sample. Let's say I dilute that sample a 1 to 10. Well, this could be written a number of different ways. We could say a 1 to 10 ratio, and basically what that means is that 1 mils have been diluted to a 10 mil volumetric flask. Okay, that's how we read that. So don't let that colon basically throw you off. It's just a shorthanded way of explaining how we diluted the sample. And then let's say that this sample that we diluted ran with a signal of 0.231. And we need to find the concentration of the original. Okay, that's the thing here. Well, in order to do this, we need a calibration curve, right? So I'm going to make my standards, I'm going to run the standards, I'm going to plot the curve, and I'm going to get a regression line. And let's say that that regression line is y equals 12.1002x minus 0.314. Sorry, let's do 0.314. Okay, well, I'm going to treat this diluted sample just like I've treated any other samples up to this point, right? I'm going to plug the signal into the equation, and I'm going to solve for the concentration. I don't treat it any differently at this point. Just the same. So y is always the signal, right? At least it should be in most cases. So 0.231 equals 12.1002x minus 0.0314. So I'm going to solve for x just like I have been doing all this time. So I'm going to add 0.0314 to each side. And I'm going to bring up my calculator again so you can follow with me. I don't want to take anything for granted, right? So 0.231. And then I'm going to add 0.0314, and I'm going to get 0.2624. All right, so 0.2624 is equal to 12.1002x. So to solve for x, I'm going to divide, right, because that's 12 times x, so we need to do the opposite of. I'm going to divide by 12.1002. So 0.2624 divided by 12.1002 equals 0.0217. I'm going to round it off, right? So 0.0217. Now, I've got to understand that this is the concentration of the diluted sample. But the question said, what's the concentration of the original? So I've got to use this concentration, and I've got to figure out the concentration of the original, because that concentration I wasn't able to analyze. It was too strong. So how do I do that? Well, let's keep in mind what we did here. We diluted, right? So the dilution equation is CV equals CV. Well, what I want to do is find the initial concentration. What was it in the very beginning before I diluted it down, right? So that's going to stay as C. I don't really know what that is. Or you can put X there if you want to, if you like that better. That's okay. Well, how much of the original did you use to dilute this sample with? Well, if I go back up here to the top, I see that that volume was 1 milliliter. So I'm going to put a 1 there. So what's the concentration that you ended up with? Well, based on the equipment, based on the calibration curve, based on the regression line, it looks like I ended up with a 0.0217. That was the purpose of me solving for that sample, right? It's telling me that the concentration of that diluted sample ended up being 0.0217. Well, what was the volume? How much of that did you end up making? Well, this tells me I ended up making 10 milliliters in total. So to solve for the undiluted, we call this a back dilution. We're trying to dilute backward in a way, right? So we're using the dilution equation. I know the final concentration, I know the final volume, and I know the initial volume. So I want to go backward to find the initial concentration. That's why we call it back dilution. So basically the only thing I have to do, C times 1 is C here. Only thing I have to do in this example is take my 0.0217 and I'm going to multiply it by 10 and I'm going to hit enter and I'm going to get 0.217 rounded off. And that is the concentration of the undiluted sample. All right. So let's say that this concentration was provided in molarity, one of the few times maybe, but let's say it was molarity. Then that means that this concentration is also going to be in molarity. So I was able to find the stronger concentration of the original sample before I diluted it by using the dilution equation. And hopefully that makes sense. Right? So let's do one more example just to make sure that we're okay with all of this. And this example, let's say that I have a sample that ran too high and I diluted it, and that diluted sample gave me an absorbance of 3, or a signal of 3.416. And I diluted this with a 5 to 100 dilution. And let's say that the equation from my calibration curve is y equals 110.341x minus 1.1134. Find the concentration of the original sample. Okay. Treat this like any other calibration curve at this point. I'm going to take this. This is my signal. My signal goes in for y, because that's typically how I make calibration curves, right? So 3.416 is equal to 110.341x minus 1.1134. So I'm going to add 1.1134 to each side. That's what my equation tells me to do to solve for x. So 3.416 plus 1.1134 equals 4.5294. So 4.5294 equals 110.341x. So I'm going to solve for x. I divide by 110.341. And x is equal to something, right? So 4.5294 divided by 110.341. And I hit enter, and I get 0.0410. I'm going to round it off that way. So this is the concentration of the diluted sample. Now, let's say that this concentration unit was parts per billion. So it's part per billion here. Now I need to figure out, well, what was it before? Right? I diluted this sucker because it was too strong. So I need to go back and I need to find out what that original concentration was. How do I do that? Well, again, keep in mind, you diluted. So CV equals CV. So what was the initial concentration? I don't know. That's what I'm trying to solve for. Well, how much of that did you use? Well, this dilution basically says you used 5 mils. So 5 goes in for that volume. Okay, well, what was the concentration that you ended up with? Well, this standard calibration curve just told me 0.0410. And what was the volume that you ended up making when you ran it? Well, this tells me it went from a 5 mil and we diluted it to 100 mils in total. There you go. So 5 times C is 5C equals 0.0410. There's that number. We're going to multiply by a 100, and I get 4.105. Right? Let's just round it off. 4.105. And then to get C by itself, I'm going to divide by 5. So C is going to equal 4.105 divided by 5, enter 0.821. That's how I'm going to round that one off. So that's the concentration as far as part per billion goes. All right, so hopefully this clears up some of the math and some of the calculations. You know, we've already talked about dilution. That was in a previous module. And this is using dilution. It's just a different perspective on it because most of the time we know the concentration we're starting with and we want to figure out how to make a weaker one, right? And that's why this is called a back dilution, because we know the weaker one and we need to go backward and we need to figure out what is the concentration of the original. So it's a dilution equation. There's no more than that. It's just the pieces of the puzzle that you have to make this equation work. We've got diluted concentration, the diluted volume, and most of the time we have the volume of the original that I've used. And we just need to backtrack and we need to figure out what the concentration was in the very beginning. And this is how we do it. All right. So hopefully these two examples is enough to go by, and that will help you out on the upcoming assignment. You'll see a couple of those questions that will be listed, and it will say, here's your signal, here's the regression line. What was the concentration of the original if we diluted this way? And keep in mind the colon. The 5 to 100, that's what that means. So it's giving you a shorthanded, abbreviated notation of how to dilute these samples. So good luck with those questions. I know it's math, but math loves you.